Thanks for having us in the crystallization pathway session, and nice to meet all of you virtually, whoever sits in front of the screen. My name is Asina Chen, a PhD candidate in the Department of Geosciences. Today, I'd like to share my study on the growth of iron-deficient hematite using time-resolved synchrotron X-ray diffraction. Crystal growth has been essential for the development of microelectronics, semiconductors, medicines, and numerous other technologies. New materials demand higher control over structural modification, homogeneity, and defect concentration. Hematite is a naturally abundant and important industrial material widely used in pigments, catalysts, batteries, water splitting devices, and many other applications. The presence of vacancies in hematite greatly enhances its efficiency as a photocatalyst, as an absorbent of radiotoxic elements, and as a charge storage capacitor. To optimize hematite performance, crystal growth processes have to be studied scientifically. Classical crystal growth theory assumes atom by atom or molecular by molecular attachment to a growing surface. However, Shortman and Murad first proposed a non-classical formation mechanism that hematite forms through ferrihydride aggregation and internal structural arrangement. Later, Peterson et al. Contributed insights into hematite growth using time-resolved X-ray diffraction. They transformed alkagoniate to hematite at a very low pH, and they reported transient hematite-like precursor with iron vacancy concentrations greatly exceeding 10 mol%. The transient phase is iron-deficient hematite, historically known as turgite or hydrohematite. In their experiments, hydrohematite was unstable and rapidly evolved to stoichiometric hematite. Hydrohematite is a highly iron-deficient hematite lying on a compositional joint between stoichiometric hematite and hematite with a composition of goethite. Stoichiometric hematite has an iron occupancy of 1.0 and a chemical formula of Fe2O3. Goethite has a chemical formula of FeOH, and hematite with a goethite composition shows an iron occupancy of 0.75. I will use the term hydrohematite to describe iron-deficient hematite regardless of its iron concentration. Is there a way to control the iron deficiency in hematite? Since the conversion from ferrihydride is the most common pathway for hematite formation in low temperature and natural systems, I prepared the ferrihydride by titrating 1 molarity of iron nitrate solution with 5 molarity of KOH to pH 10 and pH 11. Then I transferred the ferrihydride gel into a thin wall quartz capillary and sealed it. The goniometer head was rotated about 5 as the reaction occurred. As iron oxide crystallized within the capillary, the X-ray diffracted from the precipitates. The diffracted X-ray beams were collected by an area detector every 30 seconds. There's a heater below the capillary to control the temperature. We covered a broad range of pH and temperature. This is a typical example of our time-resolved X-ray diffraction pattern at 90 degrees C and pH 11. The x-axis is 2 theta, and y-axis is the time, and the z-axis is the intensity. The experiment started with ferrihydride gel with those 2 broad peaks. With time, ferrihydride transformed to hematite, marking red, and goethite, marking yellow. The transformation was completed in 1.5 hours. For every diffraction pattern, we use Rietveld structure refinement to analyze the crystal structure. For this study, the most critical parameter we aimed to refine was iron occupancy. Stoichiometric hematite can be readily distinguished from hydrohematite using X-ray diffraction. These are simulated X-ray diffraction patterns of a hematite and hydrohematite. Although their peak positions are the same, but the peak ratios are different. A simple way is to look at these 2 peak ratios. At 90 degrees C and pH 11, we found that the iron occupancy in hematite increased from 0.65 to 0.84 within the first half hour and stabilized at 0.84 for the next couple of hours. So we are confident to say metastable hydrohematite formed instead of hematite within our experimental time. This trend happens in other alkaline conditions as well. Here are the iron occupancy changes during the hydrohematite growth at pH 10, 80, and 90 degrees C. Now let's compare our data with Peterson's data. Why did hydrohematite form as the end products in our system instead of stoichiometric hematite? Peterson et al. Used alkagoniate as the reaction precursor in very acidic solutions. However, in our experiments, we found that hydrohematite persisted using ferrihydrite as the precursor in alkaline conditions. So why are the iron vacancies retained in hydrohematite at high pH? The hematite structure has sheets of oxygen anions which are hexagonally closely packed, and the iron fills 2/3 of octahedral sites. Here is an iron octahedron where iron sits in the center. Hematite can accommodate small concentration of hydroxyl through the substitution of iron 3+ by 3 protons. As more hydrohematite precipitated, the iron concentration increased. The longer FeO bond shortened, and the shorter FeO bond expanded. The trend suggests protons prefer to bond with the O1 oxygens to form hydroxyl groups, and the deprotonation results in a shortening of the longer FeO octahedral bond length. We had discovered that when iron occupancies were less than 0.8, the hydrohematite structure showed extremely distorted octahedra due to the hydroxyl in the longer FeO bond. The deficient hydrohematite will evolve to symmetrical octahedra with time until metastable hydrohematite is formed. When metastable hydrohematite transforms to stoichiometric hematite, the octahedra distorted again due to the iron-iron repulsion. One thing that I want to note is the crystal sizes of our synthetic hydrohematite were tens of nanometers. The crystal size plateau has a rough correspondence with the iron occupancy achieving the steady state. Our interpretation is that nanoparticles can retain deficiencies better than mature and well-developed crystals. We are very excited to find that our synthetic hydrohematite has a very similar structure to the naturally occurring hydrohematite. We have synthesized the hydrohematite that has the same degree of octahedral distortion and iron occupancy compared to the natural hydrohematite. Now we can make hydrohematite without the goethite impurities. We observed the particle morphology of our hydrohematite end product using scanning electron microscope. Hydrohematite particles were very aggregated and compacted. We suggest that the decrease in iron vacancies were accomplished by the aggregation and the growth of hydrohematite nanoparticles. The main takeaway messages are hydrohematite can sustain a significant concentration of iron deficiencies without breaking down or changing the structure. Unlike classical growth mechanism that involved the attachment of atoms to the surface of stoichiometric crystals, hydrohematite involves through the infilling of interior vacancies through the diffusion of superficial iron during the crystal growth. We have synthesized hydrohematite that is isostructural with natural hydrohematite. The formation of hydrohematite involves from a very deficient structure and stabilizes at an iron occupancy of 80 to 90%. This metastable hydrohematite exhibits the most symmetrical octahedra compared to the deficient hydrohematite and the stoichiometric hematite. At last, thanks Jessica for the in situ synchrotron experiment, and thanks to National Science Foundation to fund this study. This is the end of my talk. Thanks for your attention. I will be happy to take any questions.